I'm going to be talking about the use of neurophysiological measures as a way of implicitly tagging media, exposure to media. The type of system that I'm talking about, I think, is fairly easy to understand. You imagine that a person goes into an art gallery and they see 4 pictures. Each of these pictures basically acts as a stimulus that provokes physiological changes in both the brain and the body. And if we can capture that information, and then we can process that information and make inferences about what's going on with the person, then what we're able to do is to make a recommendation about what is going on with this person. So which pictures they like and which pictures they don't like. So by implicitly attaching tags, whatever they may be, to media, this opens up the possibility for things like personalized media guides or interactive narratives in the cultural heritage sector, and of course things like preference monitoring like you'd see on things like Netflix and Amazon. This project, this particular piece of work grew from a project in the cultural heritage sector where we were looking at creating an adaptive form of AR to be used during visits to museums and galleries in order to create a personalized and adaptive form of curation. So in order to work in that kind of environment, we, the people who were developing the physiological computing component, had to work with a number of constraints. First of all, it was decided that the way that we would classify the user state would be subject dependent. So we're going to create a classification algorithm for each individual person. Secondly, the classification algorithm will be trained on the spot for each instance of usage. And finally, because people need to walk around, we only used ambulatory sensors, so sensors that people would wear on the body and stand up and walk around using. The next problem, or the first problem we faced, was what kind of psychological state do we want to measure in a cultural heritage setting? We considered the usual suspects. We thought about things like mental workload and different categories of emotions, but we felt that we needed something that incorporated elements from both cognition and emotion. So the thing that came closest to what we wanted to use was interest, the concept of interest or curiosity, because we felt that when people go to gallery spaces and museums, they're looking for stimuli that will drive their curiosity and want them to explore more about that particular thing. So we had a look at the literature, and what little literature there was out there, we managed to devise a 3-component model of interest based around this, which has 3 elements: cognition, activation, and emotion or valence. The cognitive element captures the level of novel problem solving or decision making that's provoked by the stimulus. And this could be due to an object being complex or being novel or being difficult to understand. And in order to measure that construct, we measured EEG activity, specifically suppression of alpha activity in the rostral prefrontal cortex, which is this area of the brain here. So we chose this area of the brain because it's associated with multimodal integration of information, and it's also associated with higher level thought. Secondly, we felt that interest also has a visceral element of stimulation associated with it, and we could measure that using sympathetic activation of the autonomic nervous system. So we measured skin conductance, and we also measured heart rate to take care of that particular element, and we reasoned that this kind of activation component would respond to both cognitive and emotional levels of stimulation. The emotional element was included after some debate and disagreement among the team, but we decided to include valence or emotion in order to capture those instances where very strong positive or very strong negative emotions were associated with high levels of interest. In order to capture this, we also used an EEG measure. We used a measure called frontal EEG asymmetry, and that's where you take the EEG from these frontal regions here and you look at the difference between the left side activation and the right side activation. And in very brief, what you generally find is that when you see more left activation, people are in a state of approach, so they want to go towards something, or they're in a state of positive emotion. So there are 3 elements that we took. Now we began, this is a study, I'm just going to reprise a study that we presented at Kiel a couple of years ago. The first study we did on this was where we took a projection of an image. This is a 16th century tiled Valencian kitchen, courtesy of one of our cultural heritage partners, and we projected this onto a wall, and we had people come into the lab, they look at this, they're wearing the ambulatory sensors, and they get 4 audio segments, each connected to a particular facet of the scene. And these audio segments are about 30 seconds long in total, And afterwards we said to people, tell us which 2 of the 4 stories were interesting to you compared to the other 2. So we got them to make a binary distinction between the high and low interest stories. And then we fed all the data into a machine learning algorithm, a support vector machine, and to try and test whether the measures could distinguish between high and low interest for the 10 people who took part in the study. And what we found was a combination of cognitive measures from the EEG and activation measures from the autonomic psychophysiology gave us a classification rate around 80%, which was encouraging given that the task is fairly passive, and also the material people are hearing was not particularly provocative. It was very much standard sort of museum information. Now at this point, in most of the work that goes on in affective computing and physiological computing, at this point this is where the story ends with mathematical accuracy. That's a thing that most people are reporting now. But what we were very interested in is to explore how do users perceive that level of mathematical accuracy when they're interacting with this kind of system. In a scenario like the one I've described, we've basically got 2 processes in play. The first process is a digital system that is quantifying the response from the brain and the body in a very simplistic way, very objective, quantifiable way, but simplistic. Is interest high or low? In parallel, we have the much less precise, much more complex, and much more hazy process of subjective introspection as people interrogate themselves as they're interacting with a particular object. So the point of this particular paper is to study the relationship between those 2 things. And I think this relationship is particularly important for interacting with these types of systems, because the type of feedback that people get will determine whether they trust the system or not, and trust is very important if this thing is doing the tagging for you implicitly. And also, if they don't trust the system, then they won't use the system in future. So I think there's a chain of connection there between feedback, trust, and continued system usage that we need to explore. And at the moment, we don't know very much about the relationship between those 2 things. So the second study was designed to specifically explore this thing, and we moved a little bit away from the cultural heritage sector, and we decided to do an experiment with real-time classification, and we created a system where the participants viewed a series of movie trailers. And our plan was to record EEG and autonomic psychophysiology whilst people viewed these movie trailers, and then to produce a binary classification of whether interest level is high or low in the particular clip that they saw. And then the results of this classification are fed back to the participant so we can assess, via an experimenter, so we can assess whether they agree with what the system says. So we're looking at this interaction between subjective perception and objective feedback. So in order to do the experiment, to build the system in real time, the study split into 2 phases. Initially, participants viewed a number of movie trailers. They watched the movie trailer, then they provided a binary rating. They just said high or low, and we collected a series of data on that in order to initially build the classifier. So that's our training phase. And this particular study was set up to train the system as quickly as possible. So we only trained it on 2 instances of high and 2 instances of low interest, which took, as I remember, about 3-4 minutes or something like that to get it trained up. After that point, we've then built a classifier, and then we have a testing phase where people watch the movie, they say whether they thought it was high or low, and the experimenter says, this is what the system thought. So they get feedback on the system's performance. To give you a little bit more detail on that, we had 14 participants, 8 of whom were female. They experienced a training phase that I've just described, and then we had this testing phase. And the testing phase was split into 3 different periods, where participants viewed 10 movie trailers. And so what we did was, after the first 10 movie trailers that they watched, then we rebuilt the classifier, and then we rebuilt it after the second batch, and so we've got basically 3 build stages, 1 after training, 1 after 10 movie trailers, and 1 after 20 movie trailers. And the reason we did this is that we wanted to explore whether mathematical accuracy, which we measured using a hold-out cross-validation procedure, varied over the course of each build. And we reasoned, our expectation was that the accumulation of training data, the more data we give the classifier, the better it would perform. So it should be doing better at the end of the run than it did at the beginning. And obviously we're interested in how people's subjective accuracy responds to that. So I'll jump straight into the results. This is the mathematical accuracy, first of all. This is an F1 value from hold-out cross-validation. And as you can see, to our surprise, classification accuracy was generally really high from the beginning, which was a little bit of a surprise. And although you can see a trend in the data, it basically falls off at build 1 and then builds up to its original level or successive builds. None of these differences are statistically significant. So we've got a trend, but not a statistically significant trend. We also measured perceived accuracy. Now, just to be clear, perceived accuracy is a proportion of times that the participant was in an agreement with the high or low interest that was classification that was made by the system. So the first thing you can see over time is that perceived classification accuracy increases over time. And that was statistically significant. You can also see that perceived accuracy is a little bit lower than mathematical accuracy as well. Now, let me unpackage some stuff about perceived accuracy, just so we're kind of clear. Is that perceived accuracy breaks down into 4 possible outcomes of true positives, false negatives, and so on. A true positive is when the person said high interest and the system also said high interest as well. Now, when we looked at these responses, the thing that we found is that this category, the high interest category, this was by far the most common response from the system. The proportion of high interest responses to low interest responses was about 3 to 1. So this was the main thing that people saw. And perhaps we shouldn't be too surprised, because obviously movie trailers are designed in order to provoke interest from people, and that both the system and the user tended to gravitate towards this category. But what it does mean is that the feedback people received was overrepresented by this category. So this was the main kind of feedback people got. And that's what makes it important, I think. Now, what you're seeing on this particular slide is those high interest, those kind of positive responses over a period of time. You can see that the number of high responses made increased over the number of builds. And what I'm also showing you there is the ratio of true positives to false positives. So this is like an error rate that you're seeing here. So what you can see is that when we initially trained the classifier, it was making an error. It was saying low interest when the person had said high interest every 3.2 responses. But then after those 10 movie trailers get fed into the classifier afterwards, then we see that the error rate falls, so then we only see an error once every 5 responses or so. So, and the reason I'm drawing this to your attention really is that I think it's this highly frequent and therefore highly visible type of event that is driving the user's perceptions of system accuracy at the interface. So, let's again look at this relationship between mathematical accuracy and subjective accuracy in another way. Now, what you're seeing in this table, in the first column there, is a series of correlations. So you can see that the correlation between mathematical accuracy, the F1, and perceived accuracy is 0.3, so not significant at all to begin with after build 1, and then it increases. So it's quite highly significant, and it's also highly positive as well. So what we're seeing there is a convergence building between what people perceive and what the system perceives. Now, also what you can see, there is a mean difference between the two. And as I said before, mathematical accuracy tends to overestimate compared to perceived accuracy. The difference on average is about 8%. So perceived accuracy is about 8% lower than mathematical accuracy, but there's a tremendous amount of variation around that. If you look at the figures in brackets on the column on your right, you can see that's the variation associated with that. So there's a lot of individual differences within this data. The kind of main take-homes I want to give you from this study are that, first of all, the F1 value, mathematical accuracy, didn't increase significantly with accumulation of training data as we expected it to. And we were surprised how accurate it was based on a very minimal training set. My feeling is that we're capitalizing on chance in this thing, that basically the system was skewed, it was imbalanced, it was skewed towards one pattern of response, and we capitalized on that in order to get high accuracy. As I've just said, mathematical accuracy overestimated compared to subject accuracy, but not by an awful lot, even though there's a lot of variation. But what the most interesting thing is this convergence that happens. So what we see is that mathematical accuracy and perceived accuracy converges over time, correlating by about 0.7 by the time of the final build. So why did this happen? It could be due to the improved performance of the classifier over time, but as we saw, the classifier didn't really change over time, so I don't think it was that. It could be an exposure effect in that participants found the system more persuasive and trustworthy over time, just simply by being exposed to what it actually did. Or it could be an artifact to do with the experiment. It could be that by the time the subjects saw the 23rd or 25th trailer, that they simply agreed with our system as a default response. As one of my co-authors said to me when I looked at the data, said, Steve, we may have inadvertently pummeled our participants into compliance by the end of this. And that's a possibility. That could have happened. So we need to do more work to kind of understand how this is happening. But what this convergence does say, it does beg a question about the interaction between feedback and subjective states of experience for this category of technology. The general way you look at this is that we train a classifier to the needs of the individual and to the responses of the individual. But what I'm suggesting is that by exposing people to feedback, we may be biasing the process of subjective introspection so that people conform with system feedback. It may be that we're entraining the user to the system rather than vice versa. And that's something that I think we need to explore. So we've made a start, an imperfect start in some ways, but we need to understand more about how people interact with these types of systems. We need to go beyond mathematical accuracy and try and understand how perceived accuracy relates to feedback and sustained and repeated usage if we're going to understand the interactive elements of these types of systems. And that's it. Thank you very much for listening.
Hi, Professor Fairclough. I'm very glad to meet you here. Actually, I'm a fan of your research.
Oh, thank you.
My research is inspired a lot by the papers written by you and your colleagues. I really like. And I have one question, maybe not related to your papers, but I really want to have your comment because, you know, physiological computing mirroring a user kind of unconscious feedback. So we consider as an objective evaluation methods. But compared to the questionnaire and interview, we know that kind of subject measurements we already consider as a ground truth. But sometimes when we write into a paper, then we use a physiological response from the users as an evaluation method to interpret user engagement and emotions. And reviews always ask, and do you have a ground truth to validate a result from measured from physiological sensors? You know, because unconscious feedback sometimes is difficult to be let to users to express. You can say you like or you don't like, but you don't know how the physiological sensor data, what does it measure from your unconsciously, you know? So sometimes I read the papers, I found that there is a correlation between the subjective measurement and the physiological sensor data. But sometimes in the studies, there is no such correlations. But doesn't mean you obtain the wrong data from two evaluation methods, because this is still an open area require our researchers to explore, because you don't know what kind of stimulus you give to the users. You don't know users are bored or users will engage. And how would you comment on this phenomenon?
Okay. Thank you for the question. I'll do what I can in the time that I've got. I think fundamentally that there's a sense of frustration, people work in this area, that there is no ground truth for any of these states that we're measuring. So we've got to look at that in terms of the dilemma is this, I think, is that if we're trying to create systems that work on this kind of technology and work on these types of measures, do we want them to conform with subjective expectations? I mean, that's what the paper is just about, that I've talked about. And I've said before in the past writings that it's important that the feedback from the system resonates with user experience so that they trust it and they want to use it. But on the other hand, if we do that, if we make it all about subjective data and nothing else, then as you kind of point out, you take away the added value of the measures because they're tapping unconscious processes that we're not aware of. And we may disagree with them. You know, they may not resonate with our experience, and that may cause us not to trust the system. So it's a very difficult balance between giving people feedback in a way that is acceptable to them and giving people feedback in a way that kind of educates them about their own states and about the kind of the introspective process without distorting that process, which is really the dilemma that we had here. So I'm not quite sure if I really answered your question, but that is all I can do, I think, in the time that we've got. But
Thank you.
Talk after this.
Thank you very much.
One more question. This is Jintao Wang from University of Pittsburgh. My group at Pittsburgh is also working on several projects relevant to how to use physiological signals to improve MOOC learning. Maybe we can have some discussions later. My question here is, I really like your idea of grouping measurement of interest into three groups. That's cognition, activation, and emotion. I also noticed that in the evaluation stage, you only have a binary label. Interested, not interested. Can you explain a little more how you use those three groups of interest and convert them into a binary decision in your evaluation. Can you talk a little bit more details about that?
Yeah, sure. I mean, as you can probably tell, the original plan was to classify each individual dimension, as we did in the first study, and then see how they combine. But what we found was that there were such differences in sensitivity between different people to those different types of measures, those different categories of measures, that we got better classification if we grouped them all together. So what we wanted to do was to have a concept that was rigorous and that kind of made sense of an array of measures that would be sensitive to what we were looking at. So we're looking at binary classification. But then when it came to the classification itself, we really felt it was easier just to throw everything into the mix together. And really to kind of, one reason for doing that is I don't think the valence, the emotion thing was giving us very much at all. So I think it was really those two other dimensions that were driving most of the classification, that you can see that. So when you say ground truth, yeah. We didn't collect ground truth data as such. What we did was did a literature review, and then we looked at what kind of psychological concepts we wanted to investigate, and then just match them up based on the lit review. But we haven't done a formal test of those things. Okay.
Thank you.
Okay.